In the late 1960s, a young Italian physicist named Gabriele Veneziano was searching for a set of equations that would explain the strong nuclear force, the extremely powerful glue that holds the nucleus of every atom together, binding protons to neutrons. As the story goes, he happened on a dusty book on the history of mathematics, and in it, he found a 200-year-old equation, first written down by a Swiss mathematician, Leonhard Euler. Veneziano was amazed to discover that Euler's equations, long thought to be nothing more than a mathematical curiosity, seemed to describe the strong force. He quickly published a paper and was famous ever after for this accidental discovery.
I see occasionally written in books that this model was invented by chance or was found in a math book, and this makes me feel pretty bad. What is true is that the function was the outcome of a long year of work, and we accidentally discovered string theory.
However it was discovered, Euler's equation, which miraculously explained the strong force, took on a life of its own. This was the birth of string theory. Passed from colleague to colleague, Euler's equation ended up on the chalkboard in front of a young American physicist, Leonard Susskind.
To this day, I remember the formula. The formula was and I looked at it and I said, you know, this is so simple, even I can figure out what this is.
Susskind retreated to his attic to investigate. He understood that this ancient formula described the strong force mathematically. But beneath the abstract symbols, he had caught a glimpse of something new.
And I fiddled with it, I monkeyed with it, I sat in my attic, I think for 2 months, on and off. But the first thing I could see in it, it was describing some kind of particles which had internal structure, which could vibrate, which could do things, which wasn't just a point particle. And I began to realize what was being described here was a string, an elastic string, like a rubber band, or like a rubber band cut in half. And this rubber band could not only stretch and contract, but wiggle. And, marvel of marvels, it exactly agreed with this formula.
As Susskind drowned his sorrows over the rejection of his far-out idea, it appeared string theory was dead. Meanwhile, mainstream science was embracing particles as points, not strings. For decades, physicists had been exploring the behavior of microscopic particles by smashing them together at high speeds and studying those collisions. In the showers of particles produced, they were discovering that nature is far richer than they thought.
Once a month, there'd be a discovery of a new particle, the rho meson, the omega particle, the B particle, the B1 particle, the B2 particle, phi, omega. More letters were used than exist in most alphabets. It was a population explosion of particles.
It was a time when graduate students would run through the halls of a physics building, say, they discovered another particle, and it fit the theories, and it was all so exciting.
And in this zoo of new particles, scientists weren't just discovering building blocks of matter. Leaving string theory in the dust, physicists made a startling and strange prediction: that the forces of nature can also be explained by particles.
Now, this is a really weird idea, but it's kind of like a game of catch in which the players, like me, and me are particles of matter.
And the ball we're throwing back and forth is a particle of force. It's called a messenger particle.
For example, in the case of magnetism, the electromagnetic force, this ball would be a photon. The more of these messenger particles or photons that are exchanged between us, the stronger the magnetic attraction.
And scientists predicted that it's this exchange of messenger particles that creates what we feel as force.
Experiments confirm these predictions with the discovery of the messenger particles for electromagnetism, the strong force, and the weak force.
And using these newly discovered particles, scientists were closing in on Einstein's dream of unifying the forces. Particle physicists reasoned that if we rewind the cosmic film to the moments just after the Big Bang, some 14 billion years ago, when the universe was trillions of degrees hotter, the messenger particles for electromagnetism and the weak force would have been indistinguishable. Just as cubes of ice melt into water in the hot sun, experiments show that as we rewind to the extremely hot conditions of the Big Bang, the weak and electromagnetic forces meld together and unite into a single force called the electroweak. And physicists believe that if you roll the cosmic film back even further, the electroweak would unite with the strong force in one grand superforce. Although that has yet to be proven, quantum mechanics was able to explain how three of the forces operate on the subatomic level.
And all of a sudden, we had a consistent theory of elementary particle physics, which allows us to describe all of the interactions, weak, strong, and electromagnetic, in the same language. It all made sense, and it's all in the textbooks.
Everything was converging toward a simple picture of the known particles and forces, a picture which eventually became known as the Standard Model. I think I gave it that name.
Professor Sheldon Glashow, Abdus Salam, and Steven Weinberg.
The inventors of the Standard Model, both the name and the theory, were the toasts of the scientific community, receiving Nobel Prize after Nobel Prize. But behind the fanfare was a glaring omission. Although the Standard Model explained three of the forces that rule the world of the very small, it did not include the most familiar force: gravity. Overshadowed by the Standard Model, string theory became a backwater of physics.
Most people in our community lost completely interest in string theory. They said, okay, that was a very nice, elegant thing, but had nothing to do with nature.
It's not taken seriously by much of the community, but the early pioneers of string theory are convinced that they can smell reality and continue to pursue the idea.
But the more these diehards delved into string theory, the more problems they found.
Early string theory had a number of problems. One was that it predicted a particle which we know is unphysical. It's what's called a tachyon, a particle that travels faster than light.
There was this discovery that the theory requires 10 dimensions, which is very disturbing, of course, since it's obvious that that's more than there are.
It had a massless particle which was not seen in experiments.
So these theories didn't seem to make sense.
This seemed crazy to people.
Basically, string theory was not getting off the ground.
People threw up their hands and said, this can't be right.
By 1973, only a few young physicists were still wrestling with the obscure equations of string theory. One was John Schwartz, who was busy tackling string theory's numerous problems. Among them, a mysterious massless particle predicted by the theory but never seen in nature, and an assortment of anomalies or mathematical inconsistencies.
We spent a long time trying to fiddle with the theory. We tried all sorts of ways of making the dimension before, getting rid of these massless particles and the tachyons and so on. But it was always ugly and unconvincing.
For 4 years, Schwartz tried to tame the unruly equations of string theory, changing, adjusting, combining and recombining them in different ways. But nothing worked. On the verge of abandoning string theory, Schwartz had a brainstorm. Perhaps his equations were describing gravity, but that meant reconsidering the size of these tiny strands of energy.
We weren't thinking about gravity up till that point, but as soon as we suggested that maybe we should be dealing with a theory of gravity, we had to radically change our view of how big these strings were.
By supposing that strings were 100 billion times smaller than an atom, one of the theory's vices became a virtue. The mysterious particle John Schwartz had been trying to get rid of now appeared to be a graviton, the long sought-after particle believed to transmit gravity at the quantum level. String theory had produced the piece of the puzzle missing from the standard model. Schwartz submitted for publication his groundbreaking new theory describing how gravity works in the subatomic world.
It seemed very obvious to us that it was right, but there was really no reaction in the community whatsoever.
Once again, string theory fell on deaf ears. But Schwartz would not be deterred. He had glimpsed the Holy Grail. If strings described gravity at the quantum level, they must be the key to unifying the four forces. He was joined in this quest by one of the only other scientists willing to risk his career on strings, Michael Green.
In a sense, I think we had a quiet confidence that string theory was obviously correct, and it didn't matter much if people didn't see it at that point. They would see it down the line.
But for Green's confidence to pay off, he and Schwartz would have to confront the fact that in the early 1980s, string theory still had fatal flaws in the math, known as anomalies. An anomaly is just what it sounds like. It's something that's strange or out of place, something that doesn't belong. Now, this kind of anomaly is just weird. But mathematical anomalies can spell doom for a theory of physics. They're a little complicated, so here's a simple example. Let's say we have a theory in which these two equations describe one physical property of our universe. Now, if I solve this equation over here and I find x equals 1, and if I solve this equation over here and find x equals 2, I know my theory has anomalies because there should only be one value for x. Unless I can revise my equations to get the same value for x on both sides, the theory is dead. In the early 1980s, string theory was riddled with mathematical anomalies kind of like these, although the equations were much more complex. The future of the theory depended on ridding the equations of these fatal inconsistencies. After Schwartz and Green battled the anomalies in string theory for 5 years, their work culminated late one night in the summer of 1984.
And it was widely believed that these theories must be inconsistent because of anomalies. Well, for no really good reason, I just felt that had to be wrong because I felt string theory's got to be right, therefore there can't be anomalies. So we decided we got to calculate these things.
Amazingly, it all boiled down to a single calculation. On one side of the blackboard, they got 496. And if they got the matching number on the other side, it would prove string theory was free of anomalies.
I do remember a particular moment when John Schwartz and I were talking at the blackboard and working out these numbers which had to fit, and they just had to match exactly. I remember joking with John Schwartz at that moment because there was thunder and lightning. There was a big mountain storm in Aspen at that moment. And I remember saying something like, that we must be getting pretty close because the gods are trying to prevent us completing this calculation. And indeed, they did match.
The matching numbers meant the theory was free of anomalies, and it had the mathematical depth to encompass all four forces.
So we recognized not only that the strings could describe gravity, but they could also describe the other forces. So we spoke in terms of unification, and we saw this as a possibility of realizing the dream that Einstein had expressed in his later years of unifying the different forces in some deeper framework.
We felt great. That was an extraordinary moment because we realized that no other theory had ever succeeded in doing that.
But by now, it's like crying wolf. Each time we'd done something, I figured everyone's going to be excited, and they weren't. So I figured by now I didn't expect much of a reaction.
But this time, the reaction was explosive. In less than a year, the number of string theorists leapt from just a handful to hundreds.
Up to that moment, the longest talk I'd ever given on the subject was 5 minutes at some minor conference, and then suddenly I was invited all over the world to give talks and lectures and so forth.
New version of string theory seemed capable of describing all the building blocks of nature.
Here's how. Inside every grain of sand are billions of tiny atoms.
Every atom is made of smaller bits of matter, electrons orbiting a nucleus made of protons and neutrons, which are made of even smaller bits of matter called quarks. But string theory says this is not the end of the line. It makes the astounding claim that the particles making up everything in the universe are made of even smaller ingredients, tiny, wiggling strands of energy that look like strings. Each of these strings is unimaginably small. In fact, if an atom were enlarged to the size of the solar system, a string would only be as large as a tree. And here's the key idea. Just as different vibrational patterns or frequencies of a single cello string create what we hear as different musical notes, the different ways that strings vibrate give particles their unique properties, such as mass and charge.
For example, the only difference between the particles making up you and me and the particles that transmit gravity and the other forces is the way these tiny strings vibrate.
Composed of an enormous number of these oscillating strings, the universe can be thought of as a grand cosmic symphony. And this elegant idea resolves the conflict between our jittery, unpredictable picture of space on the subatomic scale and our smooth picture of space on the large scale.
And it's the jitteriness of quantum theory versus the gentleness of Einstein's general theory of relativity that makes it so hard to bridge the two, to stitch them together. Now, what string theory does, it comes along and basically calms the jitters of quantum mechanics. It spreads them out by virtue of taking the old idea of a point particle and spreading it out into a string. So the jittery behavior is there, but it's just sufficiently less violent that quantum theory and general relativity stitch together perfectly within this framework.
It's a triumph of mathematics, with nothing but these tiny, vibrating strands of energy. String theorists claim to be fulfilling Einstein's dream of uniting all forces and all matter. But this radical new theory contains a chink in its armor.
No experiment can ever check up what's going on at the distances that are being studied. No observation can relate to these tiny distances or high energies. That is to say, there ain't no experiment that could be done, nor is there any observation that could be made that would say, you guys are wrong. The theory is safe, permanently safe. Is that a theory of physics or a philosophy? I ask you.
People often criticize string theory for saying that it's very far removed from any direct experimental test, and surely it's not really a branch of physics for that reason. And my response to that is simply that they're going to be proved wrong.
Making string theory even harder to prove is that in order to work, the complex equations require something that sounds like it's straight out of science fiction. Extra dimensions of space.
We've always thought for centuries that there was only what we can see. You know, this dimension, that one, and another one. There's only 3 dimensions of space and 1 of time. And people who've said that there are extra dimensions of space have been labeled as, you know, crackpots or people who are bananas. Well, string theory really predicts it.
To be taken seriously, string theorists had to explain how this bizarre prediction could be true. And they claim that the far-out idea of extra dimensions may be more down to earth than you'd think. Let me show you what I mean. I'm off to see a guy who was one of the first people to think about this strange idea.
I'm supposed to meet him at 4 o'clock at his apartment on 5th Avenue and 93rd Street on the 2nd floor. Now, in order to get to this meeting, I need 4 pieces of information. 1 for each of the 3 dimensions of space, a street, an avenue, and a floor number, and 1 more for time, the 4th dimension. You can think about these as the 4 dimensions of common experience. Left, right, back, forth, up, down, and time.
As it turns out, the strange idea that there are additional dimensions stretches back almost a century. Our sense that we live in a universe of 3 spatial dimensions really seems beyond question.
But in 1919, Theodor Kaluza, a virtually unknown German mathematician, had the courage to challenge the obvious. He suggested that maybe, just maybe, our universe has 1 more dimension that for some reason we just can't see.
Look, he says here, I like your idea. So why does he delay?
You see, Kaluza had sent his idea about an additional spatial dimension to Albert Einstein. And although Einstein was initially enthusiastic, he then seemed to waver and for 2 years held up publication of Kaluza's paper.
Eventually, Kaluza's paper was published after Einstein decided extra dimensions were his cup of tea. Here's the idea. In 1916, Einstein showed that gravity is nothing but warps and ripples in the 4 familiar dimensions of space and time. Just 3 years later, Kaluza proposed that electromagnetism might also be ripples. But for that to be true, Kaluza needed a place for those ripples to occur. So Kaluza proposed an additional hidden dimension of space.
But if Kaluza was right, where is this extra dimension? And what would extra dimensions look like? Can we even begin to imagine them? Well, building upon Kaluza's work, the Swedish physicist Oskar Klein suggested an unusual answer.
Take a look at the cables supporting that traffic light. From this far away, I can't see that they have any thickness. Each one looks